Okay, so basically we're looking at the figure here, which is assignment 9, and it's problem 672, no? All right. So I'm just going to copy the figure the way you have it there, but let me just show you my page first. So basically this is what I have. And now let's just both of us copy this figure, okay? And then we read the problem. So the figure shows data for a portion of a ducting in a ventilation system operating at steady state. So we have this, looks at the middle. Okay. Okay, so it looks like on a 1, so the ducts are well insulated, meaning what? That is not exchanging heat, and the pressure is very near 1 atmosphere throughout the volumetric flow rate. Okay, so basically there is no change in pressure, no? Everything is P. All right. And steady state is steady state, so means the same amount of mass is coming into the system that is leaving. So let's see what they give us. So this is 1. 2 is also going in. And 3. Okay, so we have 3, 1, 2. AV1 volumetric flow rate at 1 is 5,000 cubic feet per minute. T1 is 80 degrees Fahrenheit. And you can say P1 is 1 atmosphere. We're using air. The substance is air with a gas constant of 0.24 BTUs LB Rankines. So again, everything is P2, so volumetric flow rate at 2 is 4,000 cubic feet per minute. T2 is 40 degrees Fahrenheit. We know the velocity at 3 is 400 feet per minute. And looks like T3 is what you need to find. But again, P3 will also be 1 atmosphere. And everything is insulation. Okay, so the volumetric flow rate entering at steady state is AV2 4000. Assume the ideal gas model for air, Cp equals 0.24 BTUs LP, and ignore kinetic and potential energy effects. So what do they give us the velocity then? V3. Okay. Is feet per minute. Also is no, V3 is feet per minute. Yeah. So is the velocity. Okay, so what do they say then? Ignore kinetic. I don't know. Okay, but a bit confusing at first at the reading, because they say assume the ideal gas and ignore kinetic and potential energy effects. So determine the temperature of the air at the exit in Fahrenheit. So we need to find T3 and the rate of entropy production within the ducts in BTU minutes Rankine. Okay, so I'm very confused with this V3 here. Okay, guys, so like I mentioned here, what I find confusing in this problem is this velocity here, no? Okay, that is putting me up, but hopefully we figure it out. Okay, so let me go to the page over here. What did I do with the camera? Did I close it off? All right, so we are here. So they say the system is steady state. So basically, this is going to be our control volume. So if they tell us that the system is steady state, what does that mean? That the amount of mass coming in should be equal to the amount of mass coming out. So in this case, this is going to imply what? M1 plus M2 should be equal to M3. Okay? Similarly, in the problem, they tell us that the system is well insulated. So what does that mean? That it will be no heat transfer. Q dot will be equal to 0. Okay? So knowing that, what can we do? So first, this is what type of system? This is a closed system, an open system. This is an open system, you have mass flowing. Okay? So let's say applying first principle of thermodynamics, or just put thermo, to the control volume above is only one. What are we going to have? We have Q dot minus M. So will be heat minus power plus whatever is coming in will be what? M1 H1 plus M2 H2. This is coming in, should be equal to what? M3 H3. Okay, so in this problem, they tell us that is insulated, so it means that the Q is 0. Is it any work done or produced by this control volume? No, so this is 0 again. So basically what we have here is M.1 H1 plus M.2 H2 will be equal to M.3 H3. Okay? Next, they tell us to use, using ideal substance assumption, which means what? That the enthalpy will be equal to, or the change in enthalpy is really the way we look at it, will be equal to Cp delta T, no? So why can we do that? It's because we are using air and the air always remains in the same state, correct? Okay, so if it remains at the same state, you can replace the enthalpy by basically temperatures. So in this case, let's say we need to solve, so from this equation here, so from star equation, we could write what? We can write H3 will be equal to what? M.1 M.H1 plus M.2 H2 divided by M3, or this will give you what? Okay, and let me not go too fast. So we can substitute H3 by Cp T3, H1 by Cp T1, and H2 by Cp T2. So by substituting, we're gonna get, so let me rewrite the equation, H3 equal M dot H1 plus M dot H2 over M dot 3 will give you what? T3, because the CP will cancel out, will be equal to M dot T1 plus M dot T2 divided by M dot 3. Okay, so what do we know from the problem statement? We know that T1 is 80 degrees Fahrenheit. So if we move that into Rankines, what would that be? Is it what, 460? I think it's 460, no? I mean, the approximation. So that should be what, 540? And I can look at what is, then we have T2 is 40 degrees Fahrenheit. So it should be 500 Rankines, sorry, 500 Rankines approximately. We can look at the solution because I know they are picky, so we can, okay, so we know that. Then what do we know? We know that M.1 is equal to AV1 divided by the specific volume. Yeah, and basically we know the same thing for M2 will be equal to AV2 divided by this one. And then what else do we know? We know what is the ideal gas relation? Here I'm going to need your help again. Is PV equal to what? R bar or no R bar? Which one have we been using? Let's check. Let's see if it shows up somewhere on the notes. R bar. Okay. And so R bar. So this will give us what? This will give you that V is equal to R bar T divided by P. Huh, interesting. So this will give you what? AV1 divided by what? R bar T1 divided by P1. And this will give you AV2 divided by R bar T2 divided by P2. So it looks like the T1 and T2 are going to cancel out, no? Yeah, I mean, once I substitute here, the T1, I know this would be, yeah, once substituting here, this would be AV divided by V, no? The T1 here and the T1 we're going to cancel out. Interesting. Okay. And then at the end, we'll know that M3 is just M1 plus M2. Pretty strange. Okay, so let's see what happens over here. Why is the camera always going away?
It's still up. It's, if you look at the bottom of the taskbar, there's a blue line underneath it.
This one here?
Go to the right. No, back to the Zoom thing. One's tab to the right.
In here?
No, go to the Zoom.
Go to the Zoom, this one.
Go right one tab. There's a blue line underneath it.
Just like a centimeter on the screen.
In here?
No,
This-
Okay, let me just do it the hard way.
I think that icon is just disappearing.
I don't see it here.
if you look at the blue highlighted one,
Yes.
to the right, no, blue highlight, to the right.
Okay, it doesn't matter. I mean, we are there, okay? So, I mean, let's substitute, but you see what I mean here about the V1? Once you substitute, it looks like the T is going to cancel out, no? So, all right, so let's see what happened. So, let's put it here. So, rewriting. T3. What do we have? T3 will be equal to, so let me just rewrite it, M1 T1 plus M2 T2 divided by M3. So that looks like M1 will be equal to what? A V1 divided by R bar T1 divided by P1 times T1. You see what I mean? Looks like it cancels out, no? Plus M2, that will be AV2 divided by R bar T2 divided by P2 times T2. And M3 oh, okay, and M3 is M.1 plus M.2. Okay, so now I see what's happening. So if we do it this way, then M3 will be equal to what? So we can do it that way. So this will be what? So M3 will be equal to what? So let's see, will be equal to A V1 divided by, so the temperatures will come over here. R bar T1 over P1 plus A V2 divided by R bar T2 over P2. So basically here what's going to happen is what? So T3 at the end will be equal to what? So it looks like all the R's, which is good, are going to cancel out. All the P's are the same now, so they should cancel out. They're all one atmosphere. So we'll be left over here. The T will cancel with this one. This T2 will cancel with this one. So it looks like at the top, we are just left with AV1 plus AV2. But you see the temperatures will be at the bottom. Divided by AV1 divided by T1 plus AV2 divided by T2. Okay, so let's do the numerical application and see what happens. And let's check the units. Okay, so numerical application. We have over here. So we'll have T3 to be equal to, let's see, AV1 was 5,000 cubic feet per minute plus AV2, 4,000. Cubic feet per minute. And here we're gonna have AV1, which is 5,000 divided by T1. Let's put it in Rankine to be safe, but I think we can also solve with Fahrenheit, but let's say it would be 540. So here we have cubic feet per minute divided by degree Rankine plus 4,000 cubic feet per minute divided by T2, which is 500. Right, so actually I could have factor out, no? we don't even need these ones here. We don't even need to do this part because this would be what? And here I could factor out by the 5,000 plus this one, no? Yeah. You see what I mean or no? So in other words, what we have done is this. That way it will be a little bit easier. So it should be equal to what? So let's see, AV1, it's just divided here, AV1 plus AV2 divided by, oh no, we could not factor out, sorry. Okay, so let's do the calculation. I was trying to factor out, but now we still need to do this calculation. So this will give you T3. We get the result in Rankines or in Fahrenheit. So we first get it in Rankines, or in Fahrenheit, you subtract 460. So what do you get? How much do you get in Rankines?
I got 521.5.
521.5. Okay. Minus 460.
61.5.
I think that was the answer, no?
Yeah.
Okay, so 61.5. Here I was trying to factor out this 5,000, but now it wasn't working. So I mean, basically 61.5, which, if I remember right, is the same as they had over here, 61.5. But again, this problem, the confusion is that V3. Okay, throw me off completely, no? Okay, so the second part is we need to determine the rate of entropy production within the DAC in BTUs, minutes, degree, Rankine. Okay. So again, I know it's there, but I don't see it. Oh, now I saw it for a second. Oh, it's that one here. That's what you were saying, no? Okay. So now we need to find the entropy production. Okay, so remember that the entropy production of the book, this sigma here for us is going to be equal to the delta Q over T plus the m dot delta S. Okay. I mean, this is the same definition. So in our case, there is no loss in heat, no? So this term is equal to 0. So this is what I call the total entropy of the universe in the textbook notation. But if we use in the class note notation, but if it was the textbook will be, so this is the one I use on the class note. This is what will be the one of the textbook. So this should be equal to what? Should be equal to m dot delta S and let's see what the delta S will be here. Okay, so let's go back to our system. So what is our system? Let me redo a quick figure here. Yeah, this exit, we have here 1, 5. And this is our control block. Okay, so what are the equations that we have? From the first principle of thermodynamics, we have Q dot minus dot will be equal to so the kinetic and potential energy, so it should be equal to m dot delta H. So for us will be m dot delta T or dt. Then the second principle of thermodynamics give us what? That delta S or ds, so delta S or ds is equal to the delta Q over T. All right. So if we combine, if Q dot is basically equal to the delta Q dot over here, I'll put here delta Q dot. So this will give us what? Delta Q. Sorry. This will give you Tds. This is the Tds relation. I substitute this delta Q. So delta Q is basically equal to Tds. The Tds minus power that is 0 will be equal to the m dot ds so when we did the derivation, we had Tds equal to mds plus the power. Okay, so this is the equation we have. So generally the work is equal to what? I think for the book it's P dV. Or we can use specific volume per unit mass, so P dV. So this means that we have Tds equal to the m dot dt minus P dV. So this gives us that the ds is equal to m dot dt over t minus P dV over t. Okay, we can use the ideal gas relation PV equal nRT. I don't know, that would be n is would be R bar or no R bar here. Not bar, okay. So basically from here you can get that P is equal to nRT over V. I'm just gonna redoing the whole derivation, okay? So this will give you that the S give you that the change of entropy is equal to m dot dt over t minus, so it gives you nRT over t dv over v. So you see the t's cancel out. So the change in entropy will be equal to m dot dt dt minus nr dv over v. Okay, so if we integrate this between S1, S2, and this between T1, T2, and this between V1, V2, what do we get? S2 minus S1, which is the change in entropy. Will be equal to m dot log T2 over T1. And here I think we also have the mass flow for the units. Because this will be number of mass over molar mass minus m over molar mass r log V2 over V1. I think I forgot the CP here on that equation.
Yeah, and I think in the solution or whatever, it gives.
Yeah, I forgot the CP here. I forgot it from the beginning. All right, so this is gonna get confusing. So basically, sorry for that, guys. Basically here, what did I do over here? The change of enthalpy is basically equal to CP. Here I forgot to put the C sub P dt, no? Because the assumption is what? Is change in enthalpy basically is equal to CP delta T. Okay, so I forgot that equation there. So this one is here. So I forgot all that CP all over the places going in here. So will be a CP here, CP here, CP here, CP right here, CP right here, CP right here. So you get MCP here, log of T final minus T initial.
What is the initial temperature for this problem? Because we have two.
Yeah, but that's the stuff that you don't have to think about initial. Don't think about T1 or T2. Think about initial or final. Okay. So now what's going to happen is that once we go to the figure in here, we need to see what is the change of the entropy between this initial and this final, and the change in entropy between this initial and this final. So it depends on which one of the tubes you go. Okay, do you see what I'm talking about? Because basically there's a fluid coming here and another one here, no? So in this case, this should be the initial, this should be the final, this should be the initial, this should be the final. Okay? Okay. All right, so just like I was saying, this is a general equation between initial and final. Now, if we look at this figure here, what are we gonna have? The total change of entropy should be equal to the change of entropy between S1 and S3, okay? And between S2 and S3. There should be m dot. So m dot 1 will be all right, so if we look at this system here, all right, what will be the total change of entropy? Will be whatever we have at the end minus whatever we have at the beginning. Okay, so that gives to me, so to me that will mean what? How much we have at the end? We have m dot 3 S3. This is how much we have at the end, and minus how much we have at the beginning in this tube and how much we have at the beginning in this tube. Yeah, does that make sense? So minus m dot 1 S1 minus m dot 2 S2. So we know that M3 is equal to what? M dot 1 plus M dot 2 S3 minus M dot 1 S1 minus M dot 2 S2. So we can rearrange this, and this will give you what? M dot 1 S3 minus S1 plus M dot 2 S3 minus S1. Now it's clear, no? At least to me. Does that make sense? Okay, this is the end, this is the final, this will be the two initial. So this is final, and this will be the initial, no? So, and knowing that the expression we just derived, which is this one here, delta S is equal to m dot Cp log T final T initial minus m R over m log T final over T initial. So we combine these two equations, combine this and this. We're gonna get page 126. So we get the total change of entropy. So this expression here will be M1 S3 minus S1 plus M2 S3 minus S1 will be equal to what? Will be equal to M dot 1 of Cp log T3 over T1 minus R over M log T3 over T1 plus M dot 2 Cp log T3 over T2 minus R over M log T3 over T2. I mean, if you want, we can rearrange this. Okay, this should be equal to what? Delta S will be equal to M1 log T3 over T1 factor of Cp minus R over M plus M dot 2 log T3 over T2 factor of Cp minus R over M Or, I mean, we can keep going as long as you want. We can factor out by Cp minus R over M, factor of M dot 1 log T3 over T1 plus M dot 2 log T3 over T2. So in this problem, what do we have? I think they gave us Cp. So look at the units. Where, and then you can do the calculation for me, where Cp is equal to 0.24 BTUs LB Rankines. Okay, here we need to be careful. M will be how much? I think it's 28.97, no? Do I need to say where it is coming from? This should be from table A1. That shouldn't matter which table is coming from. So it doesn't matter which book. So if you go, we can go. It doesn't matter. It's the same for English units or not, but table A1 is the one that gives you the molar mass for different substances. Air is 28.97. Okay. Now, what is R for English units? That one should come probably from what I gave you at the beginning, properties or units. This one here is probably R is over there. No,
It's on the bottom.
it's at the bottom. So in English units, we need to be careful. Okay, so 1.986, no? We can put where R for us will be careful, here is R bar, but for us is R is 1.986 BTUs LB mole Rankines. Okay. M1, I think we calculated M1 in the first part or not? We did not calculate M1 because we simplified the equation. But what would be M1? M1, we'll have to calculate it. M1 will be equal to A V1 divided by, be careful here, R bar T1 divided by P1. M2 will be A V2 divided by R bar T2 over P2, where in this case, be careful, give here the result, but where R bar will be equal to what for us? R divided by M. Yeah, because you need, basically the universal gas constant is valid for any gas, but you need to use it for a specific gas, no? So when it's for a specific gas, you need to divide by this one. So if you want to do the calculations, go ahead, but basically that's what it is, okay? So the reason I did this problem from really, I rederive everything is for you to do like a review of what is the change in entropy, no? I did not go and look at the book at a equation, no? I kind of rederive it, showing the understanding. So again, for the homework, it's not important, but if you have an exam, I want to see some of this work. Does that answer your question for the homework problem or not?
Yes.
And it's kind of different than the one they give on the solution manual, but it should give you the same answer. They are equivalent. Okay, so be careful here with the units, because this is now 1 atmosphere. You're gonna have to transform that into kilopascal, but you can say that 1 atmosphere is, I don't know what it would be in English units. Okay. Do they give us that on the units page? On the units page?
Yeah, at the top.
They give you at the top. So 1 atmosphere. So 1 atmosphere, be careful, will be, they give us that in bars. Oh, 1 atmosphere would be 14.696 lbf inch square. But some of the other units, I think the AV was in feet, no? So be careful with all the units. I know it's a pain, all those units, okay? Because you have this in feet, but in this problem you have the AVs were given to you in inches. The P is in inches, but this will give you in cubic feet, no? So you need to transform those units over. So I'll let you do the numerical application on your own. And probably I lost you somewhere on the derivation, I'm guessing, okay? But go back and try to understand what I did. We still have 3 minutes, so maybe let's go back, okay, very quick. Because I know I went back and forth, so 123, 125, 126. Let's go slowly on what I did. Because this is the part that threw me off, is the velocity at the beginning, but then. All right, so we have this problem. So basically, steady state means that the amount of mass coming out, we should be equal to the mass coming in. We use the first principle of thermodynamics. We know that the system is insulated, so the Q is 0. There is not really work done by this system or work done on the system, no? On the control volume. So this is 0. So at the end, we know that we go through this equation. I don't think you have any problem. But they say that we can use the ideal substance assumption, which means that you can substitute the change in enthalpy by Cp times the change in temperature. So basically means H3 equals Cp_T3 and so on and so on. So if we substitute into this equation here, we solve for H3. This is this equation solving for H3. We can rewrite this because the Cp will cancel out or not. They will not cancel out at the bottom because it's not at the bottom, no? It's good that we review this one. You see what I mean here? So maybe let's go back to this. You go in green, not in red. So this should be what? M Cp T1 and Cp T2. I was going too fast. Divided by M3.
Yeah, then you have a CP at the T3, right?
And you have a Cp at the T3, yeah. So they will, at the end they cancel out, but I mean at the end they all cancel out. So if you want, you can cancel it out over here if you want, okay? They cancel out at the end, but if you want to be accurate, you have the Cp there. But anyway, that's not the part I wanted to go through, is really this part over here. So we found the temperature to be 61.5 or 521. So now, the part I want really to go through is the entropy production. So the total change of entropy, what they call in the textbook, is what I call in the class note the increasing entropy of the universe, which is equal to what? Change entropy with the surrounding plus whatever is happening within the system, okay? Within the control volume. In this case, since the system is insulated, there is no change of enthalpy with the surrounding, okay? But if the system was not insulated, you have one term here. So basically what it means is that our full change of entropy or increase in entropy will just be equal to whatever is happening within the control volume. Okay, so here's where I stopped. I knew that. But now I needed to find out for our system, what is the change in entropy equal to? So I'm just looking at the delta sub S. So what I did, I kind of rederived the Tds relation, which is what? I just rewrote the first principle of thermodynamics, power minus heat minus power equal to the change in enthalpy. And I know the change in enthalpy is equal to m Cp dt. Okay. Then I write the second principle of thermodynamics, which is change of entropy is equal to the change in heat divided by the temperature. I say that this delta Q is basically equal to this Q, and I write this on the TDS. So if I replace TDS into the first equation, what do I get? TDS minus power of work equal to M Cp dt. So I get TDS equal mCp dt plus the work or the power. We know that the work done is equal to PdV. So I get this plus PdV. I divide by T. I use the ideal gas relation to write P as nRT over V. So I give us nRT over V. Basically, you end up here mCp dt dt, and here you're going to end up minus n R dV over V. Okay, so I write this, we integrate, we get this, but we don't know the volumes. I reuse the ideal gas relation, maybe I could have done it here, to rewrite the volumes as the ratios of the pressure. So that means that the volume will be equal to P, the volume will be equal, sorry, to nRT divided by P. The pressures are equals, nRs are equal, so basically this is just equal to the ratio of T2 over T1. So I substitute back into this equation, and we get that the change of entropy is equal to mCp T final minus T initial minus mass flow R over M T final over T initial. Now, the part that I was getting a bit confused is what is the total change at the end of entropy? Is scratch this line over here. Is the amount of entropy that we have at the end leaving through the tube, M1, so M3, S3. Oh, so it was good, sorry. That line was good. So M3, S3, so this is good, which is M1 plus M2 times S3, minus whatever is initially on the part of the tube 1 and the part of the tube 2. So this equation is good, okay? This one is good. And basically, we get the same expression that they have in the solution. But I will write now this delta S using this equation that basically give us this. Cp can factor by Cp, Cp T3 T1 minus R over M T3 T1 for the first term. And this term will be M2 times this one. And you just do some algebra. Okay? So it's good. Please come back to class with problems. I'd rather go through this stuff with you. Okay, if you have issues, and then if you don't have any problem, we can move into new material. All right.
Will the exam be stuff like this, or will it be stuff more like the cycle?
I mean, this is part of the homework. You could have something like this. But I mean, obviously, you're asking me the problems where you have problems on the homework, no? But I mean, yes, you could have something like this on the exam. But your question is motor cycles. You probably, if you have 3 problems, probably you have 1 problem about this and 2 problems about cycles.
What date is our final exam?
I'm not sure. I mean, I think whatever is posted, but since this is the online stuff, probably, you know, they're gonna have one day posted, but probably we're gonna do like the other ones. I leave the exam open a couple of days.
Yeah, like a window.
Like a window, yeah. So I don't think we are really limited by whatever date they post. I'll probably leave it open a couple of days, 2 or 3 days. Okay. Yeah, a good one. I think you probably got a bit confused today, no? With all the derivation. Just a little bit. Just a little bit. But sometimes it's good to get a bit scared. That way, you know you need to study a little bit more, no?
Yeah. Have
Yeah.
a good day.
Yeah, have a good day. Have a good one.